Hi, welcome to chemical bonding. In this unit, you will focus on how to determine what type of bond will form between groups of atoms, whether it's an ionic bond or a covalent bond, and within those bonds, how are the atoms arranged. So we're going to start with spending a lot of our time on covalent bonding, which forms molecules. And then we'll focus on how the ions are arranged in an ionic crystal, which is the ionic bonding. If we have time, we'll get into metallic bonding. And then we're also going to look at the geometry of covalent bonding, and we're going to put all that together. So where you see 6,5 is going to actually be up with 6,2. So today's lesson is going to focus on how you differentiate between what is an ionic bond and what is a covalent bond. And how do you determine that using electronegativity? You saw electronegativity in the last unit. How good is an atom at attracting electrons? Well, the god or goddess of the periodic table is fluorine. Everyone's attracted to fluorine, so fluorine's very good at attracting electrons. Poor little francium in the bottom left corner of the periodic table, not so good at attracting electrons. So they have very low electronegativity values in that lower left section of the periodic table. The upper right section has very high electronegativity values. They're very good at attracting electrons. And then how can we use electronegativity to identify the bond type that will form? Is it ionic or is it covalent? When you have a mutual attraction between the nuclei and the valence electrons, remember the nucleus is positive, the valence electrons are negative. When you have that attraction, that is basically what forms a chemical bond. The goal is to become more like a noble gas. They want to obtain an octet of electrons in their outermost energy level. And they do that by either gaining electrons, losing electrons, or they can share electrons. And you know back when you were in preschool and when you were younger, do all kids share equally? Not always. Sometimes they share equally, but sometimes they don't share equally. So a couple things can happen during a chemical bond, as I just mentioned. You have those bullies that just take things away, and they do not like to share. And they will gain electrons. Fluorine's kind of like a bully sometimes like that. So is chlorine, nitrogen. They don't like to share. Sometimes they do share, but in the case of gaining or losing electrons, when they're forming an ionic bond, they do not share, they will take. And that forms what's called an ionic bond. Those same elements can also share electrons very nicely when they feel like it, and that would be a covalent bond. And they will share either equally or unequally. When you have an atom gaining electrons, taking electrons away, they're usually taking from a metal. The nonmetal takes from the metal. Sharing electrons occurs between the pairing that are like each other, and that's through the nonmetals. We're going to start with ionic bonding today. Just briefly remember, this is the structure of sodium chloride. And you know that formula to be NaCl. Sodium chloride is an ionic structure. It's made up of the cations, which lost electrons. So look at sodium. Is sodium a metal or a nonmetal? Where is it located on the periodic table? Sodium is in group 1, which is to the far left of the periodic table, and that is going to be where our metals are located. So sodium is a metal. We also have chlorine in this structure, which is an anion. It gained electrons. It has a higher electronegativity value than sodium does, so it took from sodium. Where is chlorine located on the periodic table? Chlorine is located in group 17. Therefore, it is going to have 7 valence electrons and needs one more. It takes one from the sodium. It is a nonmetal. It's a halogen. Notice what happens to the size of the ions whenever they gain or lose. Pay attention to that. Look at what happened to sodium. Sodium lost electrons. Therefore, the size of the ion is smaller than the initial size of sodium. Chlorine gained electrons. Therefore, it is larger than the initial size of the neutral chlorine. Again, remember that the formula for sodium chloride is NaCl. Look at the structure. Do you see just one sodium and one chlorine? This is the structure of sodium chloride. I do not see just one sodium and one chlorine. What we call this structure is called a crystal lattice. Ionic bonds form crystals. Since you don't see just one sodium and one chlorine, then how is the formula for sodium chloride NaCl? Well, what that tells us is that in that crystal lattice, the ratio between the sodium and the chlorine is 1:1. One sodium for every one chlorine. If I took a hammer to this structure, it would shatter because it's brittle, and you would still have in the smaller crystals a ratio of one sodium to one chlorine. That chemical formula for an ionic compound is called a formula unit. What you're seeing in NaCl itself is the ratio of the atoms in that crystal lattice, not the actual number of sodium and chlorine in that structure. It is the ratio of the atoms in the crystal. Versus covalent bonding. In covalent bonding, the chemical formula is the exact number of atoms that you see in the structure. You can have one molecule of water, and you'll have 2 hydrogens and an oxygen. You can have one molecule of glucose, C6H12O6, 6 carbons, 12 hydrogens, 6 oxygen. This is not a ratio. It is the exact number of atoms that are found in one molecule of a covalently bonded structure. In covalent bonding, you're going to share the electrons. In the above diagram, you can see there are 2 shared electrons between those 2 atoms. But the sharing might not always be equal. It's going to be close to equal, but it might not always be equal. So we have equal or somewhat equal, and then we have unequal sharing, and that's going to differentiate what type of covalent bond is actually forming. In this case, in the above, each element came with its own number of valence electrons, and then it's going to share some. So in this case, it's sharing 2 valence electrons. And if you count the number of atoms between its own ring and the 2 that are shared, each atom has a number of 8, which makes it an octet and stable. This one came with 7 valence electrons, and then it shares that one other one from the other atom for a total of 8. This one also came with 7 valence electrons, and it shares the electron from the other atom for a total of 8, which makes these 2 stable. So we have equal and unequal sharing in covalent bonding. This is equal or close to equal, not polar. No one's pulling the toy more than the other one is. They're kind of sharing pretty closely. Now, hydrogen, they both have the same electronegativity values, so they're going to be equal in this partnership. This is going to be equal or very close to equal, which means that their electronegativity values are going to be very close to one another. Or we can have an unequal sharing. They're sharing still, but fluorine is definitely pulling those electrons more from the hydrogen, and you can see the direction that the arrow is pulling. Those symbols that look like almost a figure 8, those are called partial positives and partial negatives. The partial negative goes to the one that is pulling more. The partial positive goes to the one that is not pulling. This is going to be an unequal sharing of electrons. This is called a polar covalent bond. You know a polar covalent bond and a polar molecule, which is water. Oxygen is more of the bully in the situation, and oxygen pulls those electrons from the hydrogen a little bit more than the hydrogens can because it has a higher electronegativity value. So how do we know, just by looking at a formula or a bond, what type of bond it is? There's a couple rules that we need to follow. We're going to look at 2 things: what type of atoms are bonding together, and what is their electronegativity values, and what's the difference between those? Remember, how well can an atom attract electrons? What is its electronegativity? Is it good at attracting electrons or not? Far right, very good at it. Left side of the periodic table, especially towards the lower, not very good at attracting electrons because they want to give those up. These rules are just general rules. I'm going to show you 2 rules, and there's some charts in your packet you probably want to refer to. You want to go in your packet to page 2 and to page 3. The sample problems that we're going to do are on page 2. This is the chart that's on page 3. What is the difference between the electronegativity values? Notice that there's a left side that shows the difference in electronegativity, numbers from 0 to 0.3, up to 1.7, and then above 1.7. And then the other side shows you what is the percent ionic character, and that just tells you how much like an ionic bond is it. Anything below 5%, it's not like an ionic bond at all. Between 5 and 50%, it's getting there, but it's still not an ionic bond. And then above 50%, it is an ionic bond. So how much like an ionic bond is it? You're going to look at the right side and look at the percentage, and where does that percentage fall? We're going to focus right now on the left side, the difference in electronegativity values. If you are at this point or below, which is 0.3 and below, it is going to be a non-polar bond. Hydrogen, in the example on the other page, each hydrogen atom has a 2.2. 2.2 minus 2.2, that equals 0. That puts us in the nonpolar covalent category. If you are in this range, between above 0.3 and up to 1.7, you are going to be a polar covalent bond. And then if the difference between the two is above 1.7, that's going to put you in the ionic bond category. That's one of our 2 roles. The other role is to identify the type of atom that is bonding. We'll get to that in just a moment. You have this chart on page 2 of your packet. Now, I know the numbers right here on this screen are not exactly the same as the one in your packet. When you find electronegativity value charts, they fluctuate slightly. So what this is showing you is the electronegativity values of the atoms. Notice we're not even including the noble gases in this chart because they're not going to attract electrons at all. But fluorine is the god or goddess of the periodic table. Everyone's attracted to fluorine. It has a value of 4.0. This is a rating scale, basically. It goes from 0 to 4.0. Fluorine's the best. Who's the worst? Look down at the bottom left corner, and that is francium. Francium's not good at attracting electrons at all. Rule number 2, what types of atoms are involved in that bond? If you have a metal, which is to the left of the staircase, and you have a nonmetal, which is to the right of the staircase, a metal and a nonmetal are going to form an ionic bond. You have a cation, which is the metal, and you have an anion, which is the nonmetal, and that's going to form the ionic bond. If you have 2 nonmetals, 2 or more nonmetals, you're going to form a very nice sharing bond. They get along with each other. They either share equally or unequally, but they're going to share, and that's going to be a covalent bond. So let's look at some examples. What you want to do is you want to pull electronegativity values from page 2, and we're going to compare those to page 3 on the chart that you just saw a few slides ago. So hydrogen's electronegativity value is 2.2, and that is a nonmetal. Sulfur's 2.6, also a nonmetal. We're going to show the subtraction between the two. Sulfur minus hydrogen. Sulfur has the higher electronegativity. You get a 0.4, which puts us in the range of the polar covalent bond because we are above 0.3 but below 1.7. Cesium, 0.8 is a metal. Sulfur is a nonmetal. So a metal and a nonmetal should put us in that ionic category, so we should see a difference above 1.7. And we do. We have a 1.8 difference, which is an ionic bond. Hydrogen is a nonmetal, 2.2. Oxygen is 3.4, also a nonmetal. So we're taking the hydrogen away from the 3.4 minus the 2.2. So oxygen minus hydrogen, 1.2 difference. And that puts us in a polar covalent bond. We are above that 0.3 but below the 1.7. Our last one is a metal and a nonmetal. 3.0 minus the 0.8 is a 2.2. We are above 1.7, so that puts us in the ionic category. Thanks for listening today, and we'll continue our lesson tomorrow.